Hey, hey, check, check. Hey, hey, 1, 2, 3. Rentre encore, Alice. Arrêtez donc de parler d'enfants, je suis plus capable.
Quand est-ce que t'en fais?
Ben, il doit être à la veille, là.
Ouais,
Elle vient de le ramasser, là. Elle l'a rentré dans son appartement, là. Il manque. Il fait des bons petits lunchs. Je vais voir tranquillement, pas vite.
On est ensemble les deux, là.
Hey,
Hey, check, 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 check. Ouais. Hey, 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 hey. Check, check. Hey, hey. Check, check. Hey, hey.
One, two, testing, one, two. 1, 2. Test de son. One, two. Un, deux, test.
port? This,
Yeah.
Is it called Thunderbolt?
Yeah, you can use mine.
Cool, great.
Assuming it works fine.
Is it on? Oh, there.
I don't need the audio.
Do you have sound now? Good.
It's quite the big room.
Sorry?
Big room.
Yeah.
Okay. All right, it detected the...
Oh.
Okay.
We may change your resolution.
Let's see what it looks like here.
Yeah.
Is your PowerPoint in 16:9?
Yeah, it's in 16:9.
Oh, okay.
Yeah.
It should.
We'll see. That looks okay?
Nope. Just a second. I'll just take a look.
They're really far away, so it's not like you can really
Yeah.
point on them.
I know it's hard to... I can't really point at it, I guess.
Yeah.
I'll probably still go like this.
Yeah, of course.
Yeah.
I think I have one instance where I would point to something and I got
That should be good.
I don't want them mirrored because I want the presenter view.
Yeah. I'm just searching the resolution. There's a shortcut for, do you know, what is it? Don't recall where. No, that's not what I want to change. I want to change the resolution.
yeah.
There's a shortcut on Mac. I don't remember.
No, it just goes to there. That's for scaled. Oh, here it is.
Yeah,
Just
here.
1280?
Yeah.
It only gives two options.
Oh, no, why?
It
Yeah,
gives
that's
12.
because it's VGA.
Yeah, I have HDMI
You want
also.
me to plug HDMI instead?
Yeah, that's fine.
Yeah, that should be better.
Do you
I
have,
almost
do you
prefer
have an
that.
adapter for HDMI as well?
Maybe at the back.
You can use this if not.
Yeah, I'm gonna have to borrow that as well.
Yeah, that
this
should
is
be
for the
better.
VGA.
Yeah.
All I have is DVS.
Yeah, me too. But,
one for
but one
Mac.
that goes from this to HDMI, that would be perfect.
Yeah, I didn't bring
Display
that
port?
one.
Yeah.
This
Okay,
is-
the same thing as that?
Oh, this looks nice.
So we all have the same port, yeah.
We all have Macs.
Yeah, I think, well, the three of us, I don't know, for Macs.
Yeah.
Full Mac
Can't
over
really-
there.
No, it's not
For the
showing.
adapter, see if it shows.
Doesn't show.
Yeah, that's me. Sorry. I forgot them.
The mode.
Let's change it there.
Excellent. Okay, very good.
Oh, nice.
Oh, there's something
Well, okay,
with the
HDMI.
sync.
You're lucky. You have a real HDMI port.
I
in
do,
there.
yeah.
I want an old MacBook. I
For
don't
that
want
reason,
any
I
of
know,
those new
yeah.
ones.
With, like, it's worse and worse. Like
Yeah.
now you have to have a dongle for everything.
Get a dongle for everything, and
It's a dongle store now.
the keyboard breaks
Yeah,
all
Yeah,
the
that's
time.
I've heard
better.
this, yeah. Oh,
Okay,
you can see
so
it
that-
there. That's
Oh,
nice.
wow.
Oh, that's nice.
It's super
I feel
cool.
like a rock star.
Oh,
with
and there's
the-
timing.
Yeah, very good. Okay, well, do you want to
So
try
leave
yours?
that here. I think, yeah, I forgot, or I haven't maybe heard his name.
You
He's
can.
bringing an
Oh, I didn't
adapter.
hear his name either.
Is that your presenter? I have.
Yes.
We have one. The
Yes,
same.
it is. Remember to turn it on. I've gotten that before where I've gotten nervous and then I was like clicking it like, why is it not working? And it just wasn't turned on.
Yeah. Yeah, I always forget to turn it off, and now I'm scared that the battery's gonna run out today.
I have extra batteries in my backpack because it's happened to me before also.
Wow. Yeah. I always had them the last couple of months when I was teaching, and now I didn't bring them.
Excellent. Here it comes. I'll let you try it out. I'll just leave this up here for you all if you need it.
Is it on? You haven't got it on. You turn it on.
Okay,
This is
So,
a-
can you
Just
record?
try.
Yes, of
Yeah.
course.
Can take this back.
Mike, Mike.
Louder, louder.
It's not the best way to do it. You may just plug it here if you want.
That's it.
Son podium, s'il vous plaît. Okay, let's take a look at that. Philippe, change input here. There we go. Okay, so it's
So,
working.
Kirsten,
Who's
you're on
first?
right? Okay, it's 2:30, guys. Well, let's
Who's
switch.
first?
Kirsten.
Okay, perfect. There you go. So I'll leave it here, okay?
The HDMI.
Um,
I'll leave this here.
All right, please come in. This is the most exciting symposium of the whole conference. The 5 Glushko winners are going to be presenting their dissertation research. Because it's being broadcast on YouTube, there will not be questions. We're going to switch really quickly between one talk and the next. Each one is 20 minutes. Okay? So, and I won't take time to introduce each person, but, well, okay.
All right, thank you, guys. All right, it's a delight to be here. Thanks so much for having me. I'm Kirsten Adam, and today I'll be presenting one chapter of my dissertation, which really focuses on the interaction of attention and working memory. All right, so we know the capacity of visual working memory is pretty starkly limited. Although there's a lot of information out there in the world, we can only store a little bit of it in working memory at any given moment. So this makes it really, really hard to detect the change in these flickering photographs that I'm showing you. But if we take working memory out of the equation, it's pretty trivial to detect the change. So in the lab, we use a simplified change detection task to try and quantify the capacity limit of visual working memory. So in this task, we ask people to remember all of these colored squares, of course, across a short delay, and then in the end, we test them on one of the squares. So is this color the same or different? All right, so since maybe not everyone in this room has seen this task before, we'll do a very short demo. So I'm going to flash some colored squares. If the color is the same, go ahead and clap. And if it's different, stomp. Okay, you ready? All right. Okay, yeah, a little hesitant, but overall good, correct? Let's make it a little bit more difficult. Okay, a lot more hesitation. There was a slight change to that color, for sure. But as you can see, when we make the memory set size or the number of objects really big, it gets really, really hard to keep track of all of them, right? And we can bring a bunch of people into the lab, and we can have them do a bunch of trials of this tasks with different number of objects, and we can get an estimate of their visual working memory capacity, which, for our sake today, is approximately the number of these colored squares that they're able to successfully hold in mind. And when we do this, we get a pretty broad distribution of capacity scores. And this has been of a lot of interest to researchers because this ability of working memory is a core cognitive ability. So your ability to do this dumb colored squares task is also predicting your ability to do things like fluid intelligence tasks and academic achievement, et cetera, et cetera. And for a long time, we've kind of had this implicit assumption about what makes these individuals different, right? So we think of our low capacity individual as having like less room to put stuff in or like fewer working memory resources, whereas our higher capacity individual just has more room to put stuff in. And for a long time, this assumption has gone untested. But an alternative explanation is maybe that these individuals actually have the same true capacity ceiling. So they're both totally capable of getting 3 objects in mind, but they're doing so more or less consistently. And we know that failures of attention are ubiquitous in whatever kind of task we're trying to do, from the very simple to the very, very complex and consequential. And so because of that, it stands to reason, it seems reasonable that failures of attention may also play a role in working memory and in performing this type of working memory task. So today I'll be walking you through this idea and testing some predictions from it. But we have one problem with the task that I just showed you, this change detection task. So this makes it really hard to tell apart very, very different cognitive states on a single trial resolution, right? So we could have 2 very different cognitive states. Let's say on one trial you didn't store anything at all, and on the other trial you did quite well, and you stored 4 out of 6, but I happened to test you on one that you didn't get. So with our behavioral metric, this is gonna have the same outcome of just being an incorrect trial. We don't have the resolution to tell these 2 different cognitive states apart. But what we can do is just modify this task slightly. So instead of asking people to just detect a change, same or different, Instead, we're going to have people report all of the items from the array. So I'm calling this a whole report task. And what people are doing is using the mouse to click at each location what color responds there. And they have to make a choice for every single location before they can move on to the next trial. So we can model guessing and the like. So kind of a 9 AFC at 6 locations. Right, and now, when we have this whole report task, what we can do is on every single trial, we can just count how many items did they get correct. And this is going to let us distinguish between trials where they got 0 or 1 versus 4, 5, or 6 correct. Okay, so first thing we want to do is just make sure, is this task measuring similar behavior to what this other more typical change detection task has been measuring in many, many studies? So we can have the same individuals do very short measures of both, and we see that they are indeed correlated. And if we look at the performance across set sizes, we can see a similar pattern of results. So on the y-axis here, I'm plotting change detection performance. So this is approximately the number of items correct out of the items I showed them. And on the x-axis is the set size. So we can see that performance improves up until 3 or 4 items and then sort of reaches this plateau. So even though I'm showing people more and more items, they're still only storing around 3 or so. And now that we've seen that this task is, quite similar to our other working memory task, now what we can do is zoom in on this question about fluctuations. So we can just give people a bunch of these set size 6 trials. So in the next data sets I'm going to be showing you, I'm having people just do, say, 300 trials of set size 6 back to back to back. And by holding external difficulty totally constant, then we can look at these endogenous fluctuations of performance. And if we're interested in this question of failures, we might first want to know, what would a failure look like in this task? We're having people make a bunch of responses, so even if they totally randomly guess, we're going to get some correct just by chance. So here's a little Monte Carlo simulation of exactly that. So if you're just completely guessing randomly among all 6 items for these 9 different color choices, more than half the time you're going to get at least 1 correct. So we're going to call any time that people only got 0 or 1 out of 6 correct, we're going to call that like a lapse or a failure of performance. And then we might want to see, A, are these lapses correlated with working memory capacity generally? And B, like, how many of them are there? Are these super frequent? But it seems kind of extreme to only get 0 or 1 correct. And here's that correlation. So we see that, yes, these lapses are correlated with working memory capacity, and there's quite a large array of individual differences. So if you look at the y-axis scale here, this is ranging from 0 to almost 40% of trials where people are just basically a chance for this task. So this is pretty striking. If we break it down in time instead and do a median split, we see that our low capacity individuals are having about double the lapses of our high capacity individuals. So can we use this story about lapses and capacity to predict the full distribution of data? So to do that, I came up with a couple of different simple models that we might imagine. So we might imagine that either people are getting their full capacity, or they're sometimes bottoming out and not getting anything at all. So if so, we should be able to create a model where people are either engaged or disengaged, and we can multiply that times the capacity. So what we're going to do is we're going to look at the mean number correct, just the average performance, blind to the underlying distribution for each participant, and we're going to change a couple of parameters to try to predict that same mean number correct, and then look at the underlying distribution and see if that actually fits the participants' distributions. So this complete lapse model has been implemented in a few change detection papers in the past as a way of dealing with attentional lapses, and we're going to set a capacity parameter of 0 to 6 items, and then on each trial we're going to randomly pull a value from this Bernoulli distribution, and the attention parameter is just going to change the relative height of these 2 bars to be relatively more engagement trials versus more disengagement trials. All right, so when we do this, if people are engaged, they're going to get their capacity, let's say 3 items for now, plus some guesses, because they're forced to make responses for all of the items on the screen, even if they feel like they don't know anything about it. So just by chance, we're going to get this sort of upper half of the distribution above capacity due to guessing inflation. Conversely, if they are in a lapse state, we're going to pull from that guessing distribution that I showed you, and we're going to get this sort of distinct bimodal pattern of data. So we can explain the same mean performance with this sort of distribution, and the question is, what does the real distribution look like? Okay, so in contrast, it might not be that people are either just totally engaged or totally disengaged. There may be this more graded engagement of attentional control. So in this model, we still have only 2 parameters. We have a capacity parameter again, and we also have an attention parameter. But now the attention parameter is dictating the shape of this beta distribution, which can be relatively more or less skewed towards this engaged state. And so now, on each trial, we're going to randomly pull an attention value from this distribution. And now we have more in-between values. So once again, if people are fully engaged, they're going to get their capacity plus some guessing. And if they're disengaged, it can be more graded, and we get more of a unimodal-looking distribution. All right, so next is the actual data. So we see that we do get a unimodal-looking distribution. And intriguingly, if we do a median split on this, we see that both the high and low capacity participants have the same modal performance, but they're relatively shifted around this mode. And indeed, when we look at the parameters from our model that allow us to fit this data, we find that about 85% of our subjects are best fit by a capacity of 3. And the remaining 15% are fit by a capacity of 4. So in contrast to the big distribution of scores we're getting from the change detection task, when we model trial-by-trial performance, what we find is that the vast majority actually are modeled by the same capacity value, and they're just differing in how often they're failing at the task or underachieving their potential. This isn't to say that these are just all or none lapses. People aren't either just totally doing the task or totally ignoring it, but it does seem like attentional engagement is strongly contributing to our estimates of working memory capacity. And this leads us to our next question, which is, when are these failures happening and why are they happening? So we can imagine one alternative explanation for why lower working memory capacity individuals are having more of these lapses. Maybe they're just really slow to learn the task and have a bunch of lapses at the beginning, or maybe they had this sort of despair effect and give up at the very end. So here we can plot performance for every subject and every trial in the task as a sort of raster plot. So on the x-axis, I'm showing you a trial number, and then each row is going to be a subject, and the black tick marks are their lapses. And so what we see when we plot all of our subjects is that these lapses are happening sort of stochastically in time, not concentrated at the very beginning or end, and we get a main effect of performance on lapse rate, but that's not interacting with time in any way. So both high and low capacity individuals are sort of regularly and unpredictably having these lapse events. Likewise, there are many points during the trial where people could fail, right? So when we just look at behavior, we just see the very end stage, like they got 0 correct and we're not sure why. Presumably, we think it's because they failed to store the items, but a bunch of other stuff could have gone wrong. So luckily for us, we can use ERPs, and we can take advantage of previously well-described ERP components to track which of these processes are actually explaining behavioral failures. So the task is very, very similar. We've just lateralized it for the sake of taking advantage of some of these ERPs. So now we're queuing people to one side of the display. So in this case, they're attending the pink side. They just encode those 6 items on the one side and report all of the items on that side as well. And this allows us just to take advantage of lateralized brain activity that's specific to encoding and remembering the items rather than just seeing a bunch of stuff on the screen. So for all of these results, I'm going to split behavior into sort of 2 dichotomous groups. Those trials that are above the mode, or these so-called good performance trials, and trials below the mode, which are these poor performance trials. And one important explanation to kind of rule out, which is kind of dumb but important, is that maybe people just were failing to comply with our task instructions on a lot of these trials. It's pretty crazy. I show you an array of 6 things, and you can't even tell me where the red one was, right? So maybe low-capacity participants are differentially like moving their eyes away from the screen or blinking their eyes at an inopportune moment. And so we can compare the proportion of poor performance trials for both of our groups of subjects before and after we remove all the ocular artifact trials from the EEG. And we find that there's no difference, which is good. It means to our eyes, participants have their eyes open and pointed at the screen. Okay, but what about when the trial actually comes up and they actually need to do this task? We might imagine this task has very predictable timing, so they know that it's coming. They get a cue, and then it's always exactly 1 second until the memory array arrives. So you might imagine that they're going to anticipatorily ramp up their attention to get ready to really well encode this memory array. And one neural signature of this that's been hypothesized to be associated with like executive attention and inversely associated with default mode network is frontal theta power. So here I'm going to plot frontal theta power as a function of time in the trial. So people get the cue 1 second before, and then the memory array comes on at 0 milliseconds. And what we can see is that even before the memory array comes on, this frontal theta power is diverging between these two conditions. And this difference in frontal theta power is actually persisting through the rest of the trial. So this indicates that even before the memory array has come up that they need to encode, there's already an indication that people might have trouble when we get to the test. Okay, then when you show them the array, they actually need to encode the items and individuate them and store them. And so one ERP component that we can use to keep track of this is the lateralized P1. So we gave people a spatial cue to pre-allocate their spatial attention to the correct side. So if they've done that, we should get a significant positive lateralized P1. And if they've failed to use the arrow cue or maybe even oriented their attention to completely the opposite side, we'd expect to see a reduced amplitude of this lateralized P1. And so we can see that in both conditions, we get a significant P1 that's significantly positive, indicating that people have successfully used their cue and have successfully oriented spatial attention to the correct side of the display. But the lateralization of P1 and spatial attention to the correct side of the display is not distinguishing between these good and poor trials. Similarly, we can look at the N2PC as an index of item individuation. And we again see that there's a significantly negative N2PC for both our good and poor trials, but this isn't distinguishing between them. So far, this suggests people are in maybe a suboptimal attentional state before the trial, but they're still successfully orienting spatial attention and individuating those items. So where is everything falling apart? And that's when we can get to this last measure here of the contralateral delay activity. So this is a sustained negative going wave that tracks working memory load. And here we are always showing them 6 items. We've divided it by good and poor performance. And we see that when they have poor performance and they're actually reporting fewer items correct, we also see a reduction in this CDA measure that's correlated with working memory load. And here's the bar graph of that, just showing that this is a significant difference. All right, so in sum, we found a couple of markers that are predicting these behavioral failures. Like frontal theta power is predicting performance even before people have encoded the array, and people are successfully maintaining fewer items in mind. But some aspects of performance are preserved, which is also important. This indicates that people aren't just totally not paying attention to the task at all. They are complying with certain aspects of the task, like effortfully orienting their attention to the correct side of space. All right, I'll just quickly sum up here. So today I've talked about how individual differences in capacity can be modeled by a mostly common capacity limit with variability and attentional control. So this is in contrast to how we typically think about differences in working memory capacity, where we tend to colloquially talk about it as a difference in the amount of resource that someone has or in the amount of space that someone has to store information. And this is also important for those of you interested in interventions aimed at improving working memory. So this suggests that maybe interventions can't push the capacity ceiling much higher, actually, and maybe what we should focus on is instead getting people to reduce the proportion of these failure trials. And maybe that's an easier goal in some ways. Instead of making you smarter, we're just going to make you dumb less often, is kind of the benchmark. And finally, we have been able to use ERPs that have previously well characterized to track different cognitive components of the working memory task. And doing so, we're able to see that poor attentional control and also a failure to keep items in active working memory storage are implicated in these failures of working memory performance. All right, so with that, I will say thank you to all my collaborators and to all of you.
Hey, okay, I'm Max Kleimanweiner. I'm going to tell you about some chapters from my thesis, Computational Foundations of Human Social Intelligence. I did my PhD at MIT, where I was advised by Josh Tenenbaum. So I want to start with the observation that cooperation is ubiquitous in the animal world. So here's an example of some weaver ants that divide tasks. Here they're making a little bridge to cross a gap in their environment. Or wolf packs that can take down prey much larger than any of the individual pack members. And then as machine intelligence becomes a reality in today's era, we are faced with new forms of cooperation between machines and between machines and humans. But human cooperation is distinct. Even a young child cooperates with a scale, scope, and sophistication that exceeds all known non-human intelligences. Toddlers barely able to walk can spontaneously help others to complete tasks. 3-year-olds can negotiate how to divide their labor fairly, and 5-year-olds can quickly solve a variety of challenging social dilemmas using turn-taking, rules, and norms. These feats are just the prelude, though, to unprecedented levels of cooperation, underlying social institutions and social contracts, such as governments, science, technology, and morality. In some cases, these cultural products involve millions of individuals who are unrelated and will never meet. And what I'm really interested in this thesis was to try to understand the origins of the social intelligence that we have, which distinguishes us from other types of intelligence, and then how to build machines that have the kind of intelligence that we have so that they can cooperate with us. So cooperation's been this amazing force for humanity. Collectively, we can all be better off if we cooperate, but it's often a challenge because individuals might be better off looking out only for themselves. This is sometimes called the tragedy of the commons. And there's been essentially a challenge for almost 40 years of how to reconcile the existence and observation of widespread cooperation across the animal kingdom with the individual logic of evolution and economic rationality. And so this has been studied quite extensively in many fields. And one place you can see this most readily is in this prisoner's dilemma setting, where it's mutually best for the group to cooperate, but it's best for each individual to compete, so we can get that tension in a very limited setting. And one of the success stories is this idea of tit for tat, or a type of reciprocity, that you start off playing cooperate and then reciprocate by playing the same action that the other person played on subsequent iterations of the game. But there's a problem with strategies like this. Even though these things like tit for tat hint at a deeper principle of reciprocity, it's really only a simple behavior. It can only play one game. It doesn't know anything about what's good for the group. It doesn't know about the payoffs or that it's even playing with another person. All it knows is that this game has a certain label, and it's going to play row 1, and then play the action index that its partner plays. The human concept of tit for tat, in particular, and reciprocity in general, is much richer than what these automata strategies are capable of representing. And if you look at progress in this area, it's really just scaling up a bunch of different behavioral reflexes to a whole different zoo, rather than a single piece or a single agent that can play all of these different kinds of situations. So what I'm interested in is reverse engineering human cooperation, and in particular understanding how we're super cooperators. How we cooperate so flexibly and robustly. And I look at this question at 3 different timescales. So first, understanding the evolutionary origins of the cognitive structures which ultimately underlie our ability to flexibly cooperate, how these structures are used to learn moral and cultural knowledge during development, and how ultimately this knowledge is used and generalized in the moment, in action, across an infinitude of possible situations, how we distinguish friend from foe or right from wrong. So let me start at the bottom, how we operate so generally and flexibly in the moment. To do that, we developed a new set of games, mostly inspired from multi-agent systems research and computer science, led by Michael Littman. And these games are really interesting for studying and understanding ad hoc cooperation. They combine the best of both worlds. They're both realistic and intuitive to people, but they can also be made formally precise, so we can build computational models that explain people's cognition that they bring to these games. So I'll just explain very briefly, each agent controls one of these circles. They decide when they want to move, up, down, left, right, and they move simultaneously. The moves take place simultaneously. If both players try to move to the same square, then only one of those players will enter that square, the other will be bounced back. Players can earn points by moving to the square that's their own color, and every time they attempt to move, they lose a point. So you got the blue agent this time he moved twice, so he lost 2, but he got 10, so the total was 8. And then the game ends when either player reaches a square of their own color. So yellow got -1 in this case because they tried to move once but didn't get anything. So we can think about, well, what would cooperation look like in a setting like this? And so one possibility is, they both go to the outside, and then we can think, well, what would competition look like? And here, yellow just goes directly for the goal while blue gets nothing. And so we can kind of go back and say, well, draw on these different strategies in this particular context. And so as we start to think about, well, okay, maybe we're just back into this prisoner's dilemma setting that we started with, but actually it's far more sophisticated, because the challenge I've already solved for you by creating this diagram. Really, you have to reason over these low-level actions and implementations, and only through thinking are you able to say, oh, that's a cooperative strategy or that's a competitive strategy. Furthermore, there's an infinite of different ways of combining these different sets of actions, and coordinating on a particular one that you want in a cooperative way is also a challenge. Now, what's cool about these games is the way that we can parameterize them. So once people understand the rules and dynamics of the game, we can create an infinite set of these possible situations, both some by hand and also through procedural generation, that allow us to explore how people's ability to cooperate in flexible ways with either the same or different partners. So if we started with the problem of how do you cooperate in a repeated prisoner's dilemma, and the answer we got was something like tit for tat, what is the problem, what does the answer look like for a game like this, where it requires reasoning across time and space, and potentially where the game could change? So there's a few computational challenges. The first is, I might decide what I want to do at a high level. So I'll decide, do I want to cooperate or do I want to compete? But then I have to ground that intention into a low-level implementation. I have to decide what actions actually realize cooperation and which actions realize competition. Planning ultimately depends on the intentions of other agents. So if I want to reciprocate, I have to decide, are you cooperating with me or not? But those intentions are not observed. They have to be inferred from sparse actions. So I have this inverse problem. I have to be able to figure out, based on your actions, what was your intention? And then finally, there's the problem of coordination. In order to be efficient, agents have to coordinate their actions. Okay, so how did we go about modeling this? And I'm going to just explain at a very high level some of the models that we built. The first is a competitive planning mode, which was based on ideas from the game theory literature on this idea of a hierarchy of best response. So given that I want to compete, what I do is I think, well, what might you do? And then I pick an action that best responds to what I think you're going to do. And you can do that many times. So you get this level k, where k is the number of levels of iteration of that recursion. But in any case, each agent's doing that in a selfish way. They just care about what's best for them. And we ground that into the language of sequential decision-making and reinforcement learning, extending these behavioral game theory ideas into these spatial temporal contexts. But there are many reasons why cooperative cognition actually might be a bit different. So some ideas on shared intentionality from Michael Tomasello, shared agency from Bratman and Searle, and then virtual bargaining from Nick Chater. And all of these are suggestive of distinct computational mechanisms that we might use for planning with others that go beyond just, I think you're going to do that, what should I do in response? And so to model this idea of a joint intention, we developed this separate cooperative planning mode, where given that you want to cooperate, what you do is you imagine the situation in a sort of view from nowhere, where you're a puppeteer, and you have the ability to control both agents. Now, control both agents to achieve a joint goal. Now, of course, there is no real group agent, there is no puppeteer, but by imagining that puppeteer, you can figure out what your puppet should do, what you should do, and just play your role in this joint plan. So we have these two modes of cooperative and competitive planning, but the question is, well, how to tie them together, when to cooperate and when to compete. And so we modeled this idea where now we're not thinking about any particular game, but just this abstract notion of cooperation and competition. And so that the ability to kind of flip between the two is going to require some kind of theory of mind, the ability to understand other people's intentions. And we used a Bayesian approach to theory of mind, where what we're asking is, given people a bunch of actions that we've observed, what's the most likely intention? Is it cooperate or compete? And we can do that by using our models of action as the likelihood of the other person's behavior. So these planning programs end up serving a dual role. They're both models of how to cooperate and how to compete in an abstract way, but they're also models of action understanding. They let us go from some observations of another agent acting to understanding what that agent's intentions were. Okay, and we can reciprocate. Now I'm going to go through the data quite quickly. Using this model, we were able to model and predict people's behavior at quite a high degree of fidelity. When we lesion this model, so it only has one of these two modes, the performance is drastically reduced, particularly in situations that are social dilemmas, so games that really pit cooperation and competition against each other. Because without the ability to switch between cooperation and competition, there's no way to do something like reciprocity. We also looked at cases where just the theory of mind component, just the ability to understand the actions of others. So participants watched people play these games. The black is the model and the colored bars are people. And in a variety of different moves, even after just a single move, people and the model make very rapid inferences about the cooperative or competitive intentions of the other agents. We looked at this in also a kind of four-way stop scenario in a bunch of other contexts. And overall, again, our model explains a high proportion of the variance in human judgments. Okay, so that's it for in the moment. We've done a bunch of other studies in this area. But I just want to quickly touch on some of the work we've done on learning, in particular moral learning. So in the previous chapter, I looked at how people learn in the moment about a particular individual. But what about acting with those who we've never met with or who will never meet again? There's 6 billion people in the world. You have to figure out how you might weight their welfare with yours. Now, the challenge of a simple way of doing that like this, which is just saying, my utility is the reward I get plus the utility of everybody else, is that you need to figure out how to weight it. And if you're just setting one parameter for each person, that's 6 billion parameters, and we don't get data on all of them, so we need something more abstract. I talked about one way of setting those weights using the idea of reciprocity in the previous study, but we know people are much richer. So what we did in this work, which I'm only going to talk about very briefly, is to posit and introduce a set of abstract moral principles that psychologists have studied for many decades, things like kin and in-group, but also more impartial principles like indirect reciprocity or value of all people. Now, so you might, instead of putting weights on individuals, you put weights on principles, which then tell you how to value individuals. And so the learning challenge becomes, how do you learn the weights on these abstract features rather than how to learn the weights on individuals? But that requires some machinery for learning abstract knowledge. So we used hierarchical Bayesian inference, which has had success in explaining how people learn abstract knowledge in general, but we apply that to the moral domain. And in other work, we showed that that can be used to rapidly learn in this moral machine data on self-driving cars, quite rapidly learn people's moral theories and make accurate predictions from less data. I also want to briefly mention another chapter that I collaborated with Toby Gerstenberg and Sidney Levine, where we looked at how moral judgments are not just a function of welfare trade-offs, but also depend on what the intention was. Was it an intention to cause harm, or was it just a side effect of an overall greater good decision? I also did, in another chapter, some work with Alex Shaw, where we looked at modeling fairness, not just in terms of trade-off, which goes beyond just trade-offs of welfare, but also having preferences on the distribution of that welfare, but also so how when we choose a welfare decision for someone, it reveals something about us, and so we care about the inferences others will make. Okay, now I'm going to turn quickly to the last general part of this talk, which was to really try to understand the evolutionary origins of some of these cognitive structures. And so again, start with this idea: human interactions are infinitely varied almost. We never play the same game twice. So instead of playing any particular game, we studied cooperation in a game engine, so a setting where the samples from this engine, the things that it produces, are these infinite set of possible games. So what I'm showing you here is kind of a generic template for a social dilemma where, and out of that comes all these different things. Some that are known, things like prisoner's dilemmas and its variants, resource allocation games, but also interesting compositions and new variants that haven't ever been studied experimentally. Because of the variation that this game engine generates, it's implausible and impractical to imagine a specific behavioral reflex or strategy for each one of these games. Rather, it seems much more likely that people are using a much more general set of principles to make decisions across all of these settings. Okay, so again, we want to think about an abstract theory of reciprocity that can work in this challenging domain. So one way we can do it is just to think about what are different agents that can at least play these games. Maybe they won't cooperate. So here's a selfish agent. It always does what's best for itself. It maximizes the reward that it gets. An altruistic agent cares about its own welfare, its own reward, but also the reward of others. But now we have to ask the question of what makes one utility function better than the others. Is it the one that's the best for the group or the one that's the best for itself? And if we think about the fact that the social world is itself adaptive, we have to model the fact that the environment's changing. So strategies which do well are likely to become more prevalent. So we have to be able to understand what how the dynamics of how these different types of social valuation are going to work. Without going into too much details, we developed a new type of agent that has a somewhat sophisticated decision-making rule. It's easy to describe, though. It says, these agents value the reward that they get themselves, but they also value the reward of others, proportional to the probability that they believe that those others have the same underlying values that they have. Okay? So it sounds circular, but it's actually not. It's circular in the way that a good person is one who cooperates with good people. So we can unpack that and unroll the recursion and get something interesting. But there's a key cognitive challenge here. It requires theory of mind. I don't observe the utility functions of other agents. I have to infer the underlying utility function that they have by observing their behavior. And again, we're going to use this idea of Bayesian theory of mind, where given a particular type of agent, we can then have a model of how that agent might make decisions, and then invert that using Bayes' rule, where we observe a sequence of actions and we want to make inferences about the type of agent that made those decisions. That requires this recursive theory of mind, and the way we've modeled that is to not just say, well, you can't just do this recursion once, because if I'm nice to A and A is nice to B, I have to be able to model what A thinks of B. So I have to be able to model higher order beliefs about other agents. So to do that, each agent in my model of other agents has to have a model of other agents, and so on. And this gets big really quickly. It scales quite poorly in the number of models, and hence model updates, and then it also just grows exponentially with the number of interactions. Furthermore, it's only approximate. It's just this approximate unrolling of time. Instead, like we did in the earlier work I showed you where we looked at joint intentions, now we're looking at something more like a joint belief. Instead of modeling what I know, he knows, she knows, we're modeling what we know. And the idea here is that instead of tracking those recursive beliefs, we can model directly all of the things that we observed in common. So I can say, what do we know, where we is different subsets of common observation? And that actually has the advantage that it becomes an exact answer to this problem of recursive belief updating. So then we can look and see, well, how well does this work? How well do these reciprocal agents do in this challenging cooperation setting? And the first thing we did was just look at the simplest case. So you're playing in this game engine environment, but you're just playing pairwise with a bunch of different agents. You only observe your own experience. And so this is sometimes called direct reciprocity. And what we show is that these agents, so what I'm showing you here is red are the selfish agents and blue are these reciprocal agents, our agents. And when you see lots of blue, that means the blue reciprocal agents are taking over in the population. So what this plot shows on the x-axis, we're increasing the amount of repetition that they're playing with. So they can, basically by the time they're playing with the same person 5 times, they can outcompete all of the selfish agents by learning who's good and who's bad. Early on, there's no cooperation when you're only playing a few rounds, but once you get a few more, this reciprocity utility function becomes rational in a certain sense. It's the best thing you could do. Sort of like tit for tat, which I'll show in a second. It's also robust to noise. Because we're being probabilistic about the inferences that we make, our agent's actually able to do quite well even when making decisions under uncertainty. Now, when we take this same model and go back into the worlds of, say, Martin Novak and the repeated prisoner's dilemma, here I'm just replicating previous results, which show as the number, so using all these behavioral reflexes, so tit for tat, win, stay, lose, shift, forgiving tit for tat, all these different variants, and this is just a replication showing tit for tat does well in this setting when there's many repeated interactions, win, stay, lose, shift does better in this setting when there's some noise on the decision making. When we add our agent into this mix, what's it going to do? We didn't design it to play well in this particular game. We designed it to play any game, but it actually outcompetes all of the other, outcompetes the selfish or defecting agents, but also all the other types of cooperation because it's able to effectively learn learn about the types of these agents from very little data. And it's able to do that even when there's noise. So you can see on the left-hand side, the red comes back, but in our simulations, the red only comes back after a very high level of noise because, again, being probabilistic about noise helps quite a bit. Finally, because, again, we're doing this inference in an abstract way, it's quite plausible that these agents would be able to integrate both what they can learn from observation as well as what they learn from their own experience playing. So we looked at a setting where players only interact with each other in a single time in a unique game. So they never play with the same player more than once. It's a one-shot interaction. But we can vary the probability that action was, or that setting was observed by everybody else. So what I'm showing you here is a case where you might need something like indirect reciprocity to get this off the ground. And what we're showing is even when agents only have one chance to interact with each other, by making their actions observable to others, you actually can get cooperation and reciprocity off the ground. Okay, so I just want to wrap up. I began with the observation about the complexity of the social world. The world is more complex than current models allow for, but using these more complex settings, I've shown that human social interactions are negotiated in the moment using abstract causal theories of other agents. They're guided by norms and morals learned throughout development, and all of these have been shaped by the evolutionary challenges of cooperation. Sometimes, when you have a more complicated problem, you end up with a more complicated solution. But we didn't just end up with something more complicated, we also ended up with something more powerful. We ended up with agents that are more powerful cooperators. This power is ultimately grounded in the computational features of our social cognition: joint intentions, hierarchical learning, and recursive theory of mind. Thank you, and thank you to Josh Tenenbaum and my committee and all these wonderful collaborators, and to Bob Glushko and the Cognitive Science Conference. Thank you.
So this should show my slides now, actually. Okay, great. So, hi, I'm Martin Meyer, and I'm going to present my PhD thesis that I did at the Humboldt University in Berlin and at the Berlin School of Mind and Brain. Can the language we speak influence how we see the world? There has been a long and really controversial debate about the idea of linguistic relativity. But if language has the potential to influence perception, I think that we run right into an even bigger controversy in cognitive science. That is, does cognition influence perception? My goal was to address these two questions at the same time. If there are top-down effects on perception, then that means that linguistic relativity could follow from this more general principle of how perception works. I want to start with a classic example of a potential top-down effect. If you haven't seen this picture before, probably all you see is a bunch of black spots. And that's going to change when I give you a hint. So from now on, you will always perceive a face in this picture. It's been working for me for over 8 years now. And so this is an instance where you can actually feel how your perception is changed, and you can't unsee that. Now, what happens in the brain when some new piece of information changes what we see? That's the actual controversial part. Either it could be that this new knowledge changes perceptual processing itself, or on the other hand, it could only change what we attend to or how our brain interprets what has already been perceived, so processes happening before or after actual perception. And this particular example is problematic because I showed you a visual cue, so that might have changed your attention and not really your perception. And that's something that I tried to, or that I actually avoided in the studies I'm going to show you. Okay, so this is about bottom-up and top-down processing. When we are presented with a visual stimulus, it is assumed that there is first there is a feed-forward sweep of bottom-up visual activation, going from simple visual representations to ever more complex representations. But our brains also have massive feedback connections, and these can carry higher level information, for example, about expectations given a current context, or object representations stored in memory, and as I'm going to show, language. The big question is, at what point does such top-down processing start to influence visual processing? So this becomes a question about timing. And to address this timing-related question, I used EEG and event-related potentials. The first 180 to 200 milliseconds are typically associated with early visual processing. We have components such as the P1 and the N1 component. Here, positive is plotted upward. In Kirsten's talk, it was downward. So the P1 is the one going up, and the N1 is the one going down. And later stages are typically associated with higher level cognitive processing. The P1 component, for example, is sensitive to low-level visual properties of stimuli such as the intensity of contrasts. And it has actually been specifically discussed in the cognitive penetrability debate, assuming that it is not influenced by cognition, except if there is a pre-cueing situation, that is when attention is pre-allocated prior to the visual stimulus. So in my studies, I avoided these pre-cueing situations and also addressed some other important challenges to the study of top-down effects, such as low-level visual differences between conditions or reliance on memory or judgments. And then my goal was to see if after controlling for all these potential confounds, we still find effects of knowledge and language in this early part of visual processing, that is the P1 and N1 component. Okay, so the first study I'm presenting deals with the question if the language you speak can influence what you see or maybe what you don't see. One important characteristic of language is that it creates or it defines categories. For example, when we divide the continuous spectrum of perceivable light into discrete categories such as red, green, or blue. And this actually differs between languages. So for example, in Japanese, green and blue are not really separated. So if you've ever been to Japan, you might have noticed that green traffic lights are sometimes blue because they mean the same thing. So Japanese has less linguistic categories for colors than English, but there are also languages with more categories. So for example, in Russian and in Greek, there is an additional separation between light and dark shades of blue. So there's not one word that would contain all shades of blue. You always have to make this distinction to talk properly. And there have been several studies testing if these linguistic differences can influence how well and how fast people are able to distinguish different colors. And in this study, we aim to do something to go a step further and see if this also has consequences for what we see in the first place. Okay, so I invited over 100 participants to our lab in Berlin, and they had different native languages. For example, we had Greek speakers who make this difference between light and dark blue using the words galasio and ble. German speakers who have one word for all shades of blue, blau. And Russian speakers, this was a replication study, who have the words goluboy and sini for light and dark blue. And now you can actually try the task for yourself. I'm going to show you a rapid series of geometric shapes, and your task is to see if one of the shapes is a semicircle and if one of the shapes is a triangle. If there is a semicircle, please remember if the round side is up or down, and if there is a triangle, please remember if it points to the right or to the left. Are you ready? All right, was there a semicircle? Can I get a quick show of hands? Most people saw a semicircle. And was there a triangle? Who saw a triangle? Like 5 people. Perfect. So if you did not see a triangle, there actually was one pointing to the right. But if you didn't see it, don't worry, you just experienced the attentional blink effect. The triangle came really shortly after the semicircle, and in that situation, we often fail to consciously perceive the second target. Those who saw a triangle might have noticed that it came in a particular color. There were 3 different experimental conditions. We actually varied the color contrast of the triangle. These contrasts were completely unpredictable and also irrelevant to do the task. The only task was to see if the triangle was present or not. But still, I expected color contrasts to make a difference in performance because more salient stimuli are more likely to overcome the attentional blink effect, and we can still perceive them even under difficult conditions. And the most salient condition in this experiment was the mixed contrast shown on the right, because the actual physical contrast between figure and shape was bigger compared to the other 2 conditions. The green and the blue contrast were measured to be equally intense in terms of the lightness difference. But of course here we have linguistic differences between the groups, so this is where I expected the crucial differences. Okay, so now let me just show you the results. All groups of speakers found it easiest to detect triangles with the mixed contrast. For German speakers, it did not make a difference if the triangles had the green or the blue contrast, as expected. And crucially, Greek and Russian speakers actually benefited from their language and detected more of the blue triangles compared to the green triangles. The effect was about 3 to 4% better than the green contrast, but I must add that the mixed contrast was also only about 5 to 8% better. So that's kind of the ceiling, because it's a bottom-up, more salient condition. Okay. So this shows for the first time that our native language affects what we do and what we don't see. But how can we know that this is actually an effect on perception and not, for example, attention or memory? It could be that Greek speakers are just better at remembering blue triangles, but they perceive them in the same in the same way. So that's where the EEG comes in. And what we see here is that there was a difference between the blue and the green contrast in Greek speakers, and actually this starts early in the P1 component that is known to reflect early visual perception. In German controls, there was no difference whatsoever between the green and the blue contrast. So this shows that linguistic color categories influence early visual processing. The next study deals with the question of causality. In the first study, we tested speakers with different native languages, but they could have differed in other aspects as well, such as their environment or culture. So in this study, I tried to do this in a more controlled laboratory setting. And I did this by showing participants these funny objects that they had never seen before. And then they learned to categorize these objects. For example, these upper two are called kalimat, and the other ones are called sonatab. So they learned to categorize the objects by name. And since all objects were unknown prior to the experiment, we could just swap the assignment. So a different participant would learn that these two on the left are called kalimat, and the other two are called sonatab. So we can eliminate any bottom-up visual differences between conditions. It's the exact same objects. And we can be sure that any differences we see in later on perception are due to the learned category knowledge and not the look of the objects. So 2 days after this learning session, participants performed a visual search task with the goal to detect as quickly as possible the deviant object in an array such as this one, and then press a button whether it was on the right or the left side of the display. What we find is that you can do this faster when the deviant object has a different name than the distractors compared to when it has the same name. So it pops out more when it's called differently. Using EEG, we find that the influence of linguistic categories again starts early. It's again in the P1 component, but only for targets shown in the right visual field that are first processed in the left hemisphere of the brain, which is the language-dominant hemisphere in most people. So the pattern we find is that early on, both in the P1 and the N1 component, there's a lateralized effect for targets in the right visual field only, and later on, matching the behavioral results, there's a non-lateralized effect in the N2 component that reflects attentional selection. Taken together, these results show that there's a causal influence of linguistic categorization on early visual perception. The last study I'm going to present took a different approach. Here we tried to kind of directly observe top-down effects while there was no relevant bottom-up input by testing the effect of knowledge on mental imagery. So here's another little task demo. I'm going to show you a small detail of an object, and your task is to later on imagine the full object. And in between, I'm going to show you a matrix of letters where your task is to find the deviant letter. That's supposed to distract you. And then after the letters disappear, you imagine the full object. Okay, are you ready? Here's the object to be imagined. Now please find the letter. And now imagine the object. Okay, that's actually pretty hard to imagine something right on cue, but with a little practice, our participants were able to do that, and we were even able to extract event-related potentials from that. So the participants did the same thing you just did. They imagined objects on this blue background, and those were well-known objects, but also, again, these funny, unfamiliar objects. And there was a learning session before where participants learned different amounts of semantic knowledge about the objects. In the minimal knowledge condition, they would only know the name of the object and nothing else. Then there was an in-depth knowledge condition where they would learn the name of the object and also its function and origin. So for example, this here is a measurement device you can use in the kitchen to measure quantities of flour and sugar and also liquids. So the cool thing about this design is that we can vary the content of mental imagery while keeping constant the visual properties of the image to be imagined. It's the exact same image, but it has more or less semantic content. And then there were also well-known objects where we don't have this visual control, but we still have a semantic knowledge increase and also more perceptual experience. Okay, so here are the results. First of all, the more you know about an object, the easier you can imagine it. Participants were more often successful in imagining well-known objects compared to all of the novel objects, and they were faster with in-depth knowledge compared to minimal knowledge. So knowing things about objects helps you to imagine them. In EEG, we find a really interesting pattern. Again, there's an effect on the P1 component, this time from semantic knowledge, and the cool thing is that we find the same effect in perception and imagery. So what we see here is zoomed in on the P1 component for the different knowledge conditions and separately for perception and imagery. And what we see is that the P1 decreases with increasing knowledge by the same amount in perception and imagery. So this provides us novel insights into the nature of both mental imagery and top-down effects. First of all, this shows that mental imagery and perception share mechanisms really early on. It's well studied and well known that perception and imagery engage overlapping structural substrates, but it has never been shown that these similarities or these mechanisms start to be similar that early on in visual processing. And second, concerning top-down effects, this gives us some hint at the mechanisms behind this, behind top-down effects. This suggests that they have to do something with simulation or predictive processing. So here are my conclusions. First of all, language and knowledge can shape what we see. And indeed, what we can take from the EEG results is that top-down influences can actually affect early stages of visual perception. So it seems that early perception is not encapsulated from cognition. And I think that with this we can also explain linguistic relativity effects. It seems that linguistic relativity doesn't have to be an extra principle of its own, but it follows from a more general principle, the possibility of top-down effects. And this helps us to reconcile universalism and relativism by showing that we don't have to freak out about linguistic relativity. It's just a consequence of cognitive penetrability. So maybe we can freak out about that cognitive penetrability. I think some people will. Okay, I really want to thank all the people who made this possible for me to come up here on this stage and present my work. My amazing advisor and mentor, Rasha Abdelrahman, the people who nominated me for this prize, Asfa Majid and Martin Rolfs, my collaborators, Romy Frömer, Johannes Rost, who came up with the whole imagery task design, and Werner Sommer, and of course the Berlin School of Mind and Brain for supporting me during and after my PhD. Thank you very much.
All right. My name is Jean-Paul Noël. I did my PhD at Vanderbilt, and now I'm mostly at NYU.
Okay, so I think that probably most people in this room will be familiar with this character, right? This is clearly your typical undergraduate student who walks into a lab, and this person is well equipped to do the sorts of experiments we typically ask undergraduate students to perform. He or she possesses a pair of eyes and therefore can do visual experiments. Now, unfortunately, probably a little bit less familiar to the perceptual scientists in the room, we have the auditory potato head too. We have the tactile potato head, the olfactory potato head, or finally the gustatory potato head, right? Now, I'm not interested in a single one of these potato heads in isolation, but I'm actually interested in this case, which is the multisensory potato head. And I'm interested in this individual for a couple different reasons. The first one is because we happen to live in a multisensory world, and therefore if we really truly want to study perception in the wild and trying to understand what it's like to have a conscious experience of anything, we might want to try to understand perceptual awareness in the general sense. And then the second reason is because I find the question of multisense integration to be a tractable problem in studying neural integration generally. And I think that as a cognitive scientist or as neuroscientists, that is what we are interested at the end of the day, right? Is how is it that relatively simple signals at the sensory periphery come, how they're transformed up the neural axis until you have this cohesive representation of the world outside of you. Right. Now, something that crystallized for me over my PhD, and the reason why I use the toy example of the potato head, is that the sensory periphery, to some extent, is plug and play. Right. So we don't think that there's a mechanistic difference between how do we integrate audiovisual, visual tactile, or audio tactile information. They just are different senses, they're different energies at the outset, and then we just transform them out of periphery. And at the central nervous system, we believe that the mechanism is more or less the same. The second concept that crystallized for me is that our sensory periphery are biological sensors, right? And that is crucial. So the cockroach here may be able to sense heat and body odor, while the bat may be able to sense air compression waves, and finally the electric eel may be able to sense electric fields. But what is critical to me is that the electric eel may be completely blind as to heat or body odor, right? So there's nothing that is intrinsically out there, but we are only able to experience that what our sensory periphery is equipped to capture from the environment, right? So this idea was, of course, or at least in the Western world, we typically attribute this idea to Van Helmont and colleagues, or just him. But it actually exists in the literature all the way back to the 11th century, and it's depicted here in this figure by this German author I'm not going to try to pronounce. But the idea is that there's some sort of features in the environment, and those may trigger some sort of receptors, which may trigger some receptor organs, and those in turn communicate with some effector organs, and that creates a first loop, which creates your inner world. And then that inner world may be able to come and affect how you interact with the world, right? And so a couple of features I like about this diagram, and the reason why I use it, is because I believe this says newer loop. You can't see my cursor, right? But anyways, the smaller loop here says inner loop, which kind of implies that the loop from perception to action and then back to perception is the older loop, right? And so my talk is going to be really divided in two. The idea here being that we might think that perception happens here, but it really doesn't. It happens really at the periphery and then also at the effector organs, right? Okay, so I'm going to divide my talk in two. The first part is what I call and my dissertation. My first part is what I call the outside-in approach to the study of perceptual awareness, and the second part is what I call the inside-out approach to the study of perceptual awareness. How is it that, what already exists in my mind, or for example, what do I bring to the table that will come to affect how I perceive the world? All right. So about the first part, why, again, the question of why study perceptual awareness from the multisensory lens? Well, first of all, as I said before, we happen to live in a multisensory world. The second, and I think that this is the critical point, is the fact that we don't have multisensory sensory periphery, right? So if I perceive a cohesive audiovisual representation of the world, there must have been some sort of integration, and that happens to be critical to all the theories of consciousness today, right? So we have theories that say, for example, that consciousness is enabled by integration, or enables integration. We have theories that say that consciousness is enabled by integration, so the opposite. And then finally, we have theories that say that there's an identity relationship between the amount of information you can integrate and your level of consciousness. Okay? And so using this multisensory approach to the study of perceptual awareness will enable us, or just gives us, all these clear examples and clear definitions for what do we mean by integration. All right. So in the first study, or the first study I wanted to briefly talk about today, and I'm not going to be able to talk about it in depth, but I basically asked this question whether the neural correlates of visual awareness, which we know to some extent, and there's a lot of work in this domain, whether those are equal to the neural correlates of auditory awareness, and in turn are those equal to audiovisual awareness, right? And if that is the case, then maybe it just means I should scrap my dissertation and start over with a new idea, because I could just borrow all the insight we have from the study of visual awareness into the more global study of perceptual awareness generally. So this was an EEG study. We presented participants with auditory, visual, or audiovisual stimuli that were titrated to be at 50%, so they were detected half the time they wouldn't. We were recording 120 electrodes of EEG, and then I basically applied a bunch of different metrics that have been set in the literature to index perceptual awareness, right? And I'm not going to be able to go into those in detail, but we looked at something I like to call latent sustained activity, which is just evoked responses. We looked at the reproducibility of responses across trials, and then we looked at a measure of neural complexity. And the take-home message of this paper is that while the neural correlates of visual awareness seem to also apply to the auditory case generally, they don't apply to the audiovisual case. Okay, so this was a little first step saying maybe I can pursue this line of research. Maybe there's something interesting about perceptual awareness in the multisensory case, right? That's more general than just the visual. Right, so then for the second study, and this is where I'm going to spend most of my time today, I tried to invert the logic there and ask whether, adopting a multisensory lens, whether I can inform current theories of consciousness. So I specifically wanted to look at two theories. The first one is what people call the global neuronal workspace theory, and this theory basically just states that, by the way, notice the visual bias, right? All activity starts in V1. So that theory says that when you're unconscious of a stimulus, your bottom-up drive isn't strong enough, and so you may have some sort of decay of activity as you go from early visual areas to higher areas, and the neural activity is really only driven by the presence of a stimulus. Now, in turn, you become conscious of a stimulus if it invokes either by itself or via top-down amplification, if that can kind of elicit some sort of recurrent network that incorporates frontal and parietal cortex, then you may be able to have a conscious experience. Right? One of the keys here being that the neural evoked response from the presence of the stimulus may live beyond the actual physical presentation of the stimulus. Okay, and the hallmark of that in our neural studies is really this idea of neural ignition. There's some sort of nonlinearity where at some point, and here it's depicted in the frontal cortex, at some point you have this neural ignition where you have this nonlinear transition where you become aware of stimulus. Okay, the second theory I want to talk about is IIT, the information integration theory, and this theory claims to be different from all the rest in that it starts from phenomenology. It poses 5 axioms that must be true of any theory of consciousness because these are the components that are true in any conscious experience. And then based on the last 2 axioms, really on information and integration, it develops a metric they call phi, and they write books about. And this phi metric is a consciousness meter. Okay? Now, unfortunately, you can't compute, I think I was reading a paper recently saying that if you have a network of over 18 nodes and you had all the computing power in the world, it would take you longer than the universe is going to exist to compute this phi metric for an 18-node network. So, difficult to test, right? So I came up with this idea coming from the multisensory lens. I came up with the idea that let's imagine we have a really simple 3-node network, which is you can compute phi in easily. And let's imagine A and B here are unisensory areas, say audio and visual, and they project to a third node, C. And the third node, I can make it an XOR logical gate, meaning that it will be active if on the previous time point, either A or B were active, but not if both were. Or that central node can be an AND gate, meaning that it will be driven by the presence of both A and B on the previous time point, right? So if you just take this logic and play this game, you can calculate phi, and what you end up with is the fact that phi triples when the center node is an integrative node, okay? So I thought I would try and test this idea and see if it holds in data. And so this is really trying to tackle the IIT theory. And so to do that, so based on this little game, we can come up with certain predictions that you can test empirically, right? So the first prediction would be, for example, that as you lose consciousness, it may be the nodes that integrate sensory information that may be most impacted. So for example, they might stop integrating. The second prediction you can make is that when the animal is conscious, these are the particular nodes that would show quote-unquote properties of consciousness to a greater extent than the convergent neurons.
Okay, and just to quickly go back to what the predictions of the global neuronal workspace theory would be, they would be that you would have longer sustained activity under the conscious states and unconscious states, and then finally we would see some sort of neural ignition, and that being the co-activation of both sensory and then higher order quote-unquote associative areas when the individual is aware compared to unaware. Okay, so to test it, I collaborated with these two individuals, and we recorded this is recording single unit data from ventral premotor and S1 while monkeys were presented with audio-tactile stimulus or just auditory stimulus. And critically, we were giving the monkey propofol, so the monkey was falling unconscious as he was doing the task. And what I'm plotting here, and I'm sorry I don't have a cursor for that, what I'm plotting here is the normalized cumulative sum of trials of a given kind, and so in the first plot what you can see is correct responses, and so you see those just kind of accumulate that at the outset of the trial. And then eventually on the last figure here, you see this is the given point where after that point the monkey doesn't respond to any of these sensory stimulus, right? So we can categorize that as being the point of where the monkey loses consciousness, and then we divide our trials as the function whether the monkey was conscious or not. Okay, so some basic characteristics of these neurons in S1 and ventral premotor. So you see that S1 responds to audio-tactile information. It doesn't really respond much to auditory, and then this is a catch trial where there's nothing happening. And then for the ventral premotor, it's an area that is known to respond to auditory stimulus, and we see that nicely here, right? Okay, but the critical point that I want to make is that in the colored you have when the monkey was unaware, and in gray faded out you have when the monkey was unaware. And so you see that for all cases, in particular, let's look at the audio-tactile and tactile case, you see that there's a more sustained response, particularly later latencies, which is one of the predictions from the global neuronal workspace. So that's a first point for that theory. Okay, then what I did is really kind of here the critical point is I took definitions of from the field of multisense integration to divide functionally neurons as either being convergent, quote-unquote XOR gates, or being integrative, right, AND gates. And you can do this. The classical definition in the multisensory field is looking at whether a neuron responds not only to like sensory modality A and to sensory modality B, but whether there's some sort of nonlinearity between when you sum A and B artificially later versus when you present them at the same time, right? And so what you can do here is I can divide my neurons into convergent, and I define that as neurons that respond both to audio and tactile versus those that integrate, which means that they don't necessarily have to respond overtly to both audio and tactile, but when you present audio and tactile together, they respond differently from what you predict by the simple sum of audio plus tactile, right? Okay. So testing the first prediction of the IIT, again, is the idea that perhaps it is the integrative neurons that would be most impacted by a loss of consciousness. And so what I did is I just took my pile of convergent neurons and took my pile of integrative neurons when the monkey was aware, and I looked at what happened to them when the monkey fell unconscious. And what you see is that actually most of the integrative neurons remained integrative, while most of the convergent neurons started responding only to touch and not to audition. So this is against the IIT prediction. Okay, the second prediction, or the second hypothesis I would like to test, is that when the monkey is conscious, it shows quote-unquote properties of consciousness to a greater extent than the convergent neurons. And I'm going to use, and in the paper I used two different measures. One is impulsive complexity, and this is the same complexity measure I used in EEG earlier. And it really just boils down, this is a measure that is championed by the IIT theorist, and it basically boils down to zipping files, right? So it's the same, this impulsive complexity is the same sort of technology that computers still use today to zip files. It's a lossless compression algorithm, and we can just see how complex is a given neural data set. So unfortunately for timing reasons today, I'm not going to talk about that, but then I am going to talk about noise correlations. So there's this nice paper that shows that noise correlations in neurons increase by 6-fold when monkeys are unconscious. And so what I'm going to do is I'm going to take all my trials and simply see whether that is true, and that's what you see on the top row here. And it looks underwhelming because of the violin plots, but there's a 5-fold increase in noise correlations when monkeys are unconscious compared to when they're conscious. And so then what I'm doing is I'm looking how does that relate to integrative versus convergent neurons. And what you see at the bottom is that when the monkey is unaware, the convergent neurons increase the noise correlation by quite a bit, but the integrative neurons stay the same. So this is again, so the property of consciousness in this case is low noise correlation, and it is or high noise correlation when they're unaware, when the monkey's unaware, and you see that being true in the convergent neurons, but not the integrative neurons. So that is again against the IIT prediction. Okay. And then lastly, oh no, Lastly is the idea of neural integration and neural ignition. And so here what I'm doing is I'm just going to take a definition, which in this case was 2 standard deviations, and I'm going to look at on a particular trial, is a particular neuron firing above its mean plus two standard deviations, right? And given the Poisson distribution of noise firing, when you set a threshold of 2 standard deviations, you get very few trials in which a neuron is considered quote-unquote active, right? But I can nonetheless still do that, and I can see them in about 10% of trials. Given an audio-tactile or tactile stimulus, the neurons will respond. You see a similar sort of effect in prefrontal cortex, and in most trials, the neurons don't respond. But then the key here is looking at neural integration and or neural ignition. This is I randomly subsample, take all my neurons that are recorded simultaneously, and I look at it on a given trial was both the primary sensory area and the prefrontal area where they both activate at the same time. And you see that coincidence or that event of neural ignition is much higher when the monkey is aware than unaware. But of course, this can just be driven by the fact that even S1 and ventral premotor by themselves are active more often. And so we can simply just look at what the expectation would be of having those 2 areas co-activated in the same trial, and then subtract that from what we observe. And what we observe is that we do have an incidence of neural ignition when the monkey is unaware, but not when the monkey is unaware. Okay. Great. So the conclusions for this first part of the study, of the dissertation, I promise the second part is way less. So we have a great number of audio-tactile multisensory neurons in S1. I went through this quickly, but there was about 40% of neurons in S1 respond to our multisensory, and that they, if you co-present an audio stimulus, they will respond differently. The integrative neurons were, quote-unquote, more resistant to propofol administration. The convergent neurons more faithfully track the level of consciousness than the integrative neurons. And so overall, the data supports the global neuronal workspace, but not the IIT. Okay, the second approach, and I promise this is going to take just 4 minutes, it comes from this is the inside out. And this comes from the philosophical argument that for you to be aware of anything in the external world, there has to be a subject to that experience. And therefore, there must be some sort of pre-reflexive notion of selfhood. And Blank and Metzinger, for example, postulate what would be some of these pre-reflexive proto-self in some ways. And so they said that you have to have a sense of body ownership, you have to have a sense of self-location, you're somewhere in the environment, and you must have a first-person perspective on the world. So I'm more interested, and I was going to look at particularly the idea of self-location. I'm going to do that by measuring peripersonal space. So there's a given set of neurons in parietal cortex and ventral premotor cortex that are multisensory. They respond to touch on the body, but also to either auditory or visual stimulus when it's near the body, but not far from the body. And I thought, and as people have predicted, that these neurons may be important for building a notion of self-location in the world. And so to measure this in humans, we adopt the following paradigm. We have audio trials where a sound looms towards a participant. We have tactile trials where the participant feels touch at given timings. And then we have an audio-tactile condition where as the sound looms towards a participant, they're given touch, right? And so the idea here is that we look at reaction times to touch. We tell that sound is task irrelevant. But what you see is that when the auditory stimulus is close to the body, you have a multisensory facilitation. You respond faster to tactile stimulus. And so we can fit this data, this RT data to a sigmoidal and extract a central point, which would be the extent of someone's peripersonal space, or we can look at the slope, which would be the gradient of someone's peripersonal space. Okay, so the first, and this is going to be really quick, we tested here the prediction that Blanke made, where he claimed that probably these neurons don't encode the physical location of the body, but they encode the location where someone perceives their body to be. So in order to test it, what we did is we immersed participants in a virtual environment where they saw themselves projected 2 meters in front of themselves. And then we gave them touch, which they saw in either synchronous and asynchronous fashion. And this is basically the rubber hand illusion, right? So when participants, when it was in the synchronous condition, participants reported feeling ownership of the virtual body in front of them, and then we measured peripersonal space in given the paradigm I just explained a second ago. And this is a summary. We basically see that in the synchronous condition, but not the asynchronous condition, peripersonal space shifts forward as to get closer to the virtual avatar, meaning that peripersonal space does seem to encode to some extent where you perceive yourself to be and not necessarily where you are. We did a second study where the incoming sensory stimulus that we used to measure peripersonal space was rendered unconscious by using continuous flash suppression, and then also the stimulus we used to elicit the full body illusion was rendered unconscious also by using continuous flash suppression. Okay, and so this is what the setup looks like in the wild, and what you see, and I'm just going to draw your attention attention to the bottom plot is where you see that also even when the participants are not aware of whether they're in the synchronous or asynchronous condition, and even when they're not aware of where the visual stimulus is it far away from you or is it close to you, you see that in the synchronous condition you have an enlargement of your P-personal space. Okay, so the conclusion, so the second part of the study is simply that P-personal space seems to encode the location of the bodily self, not necessarily the physical body. It does so in a pre-reflexive manner. That was the point of the second study, to rendering all these things unconscious. And then I just want to highlight a couple other studies. So we've shown that via an ECOG study that these P-personal space neurons truly are multisensory, which hadn't been shown either in the neurophysiology literature. And then finally, we just derived the EEG correlates of this task, and we showed that when applying that metric to a group of comatose patients or patients with cognitive motor dissociation, so these are groups of patients that are equal for motor output but different for levels of consciousness, we can dissociate between these two groups by measuring P-personal space. Okay, thank you for your attention, and I won't take questions. Okay.
Okay, great. I'm Catherine Tillman. I'm happy to tell you a little bit about my dissertation work, Constructing the Concept of Time, which I conducted at UC San Diego. So the question of time has fascinated scholars from all sorts of different fields for centuries, and part of why time is so interesting is that it's perplexing and it's paradoxical. And one of those paradoxes about time is that it's simultaneously deeply experiential. So we seem to live our entire lives in time. All of our events that we see, all of our mental acts, they all seem to take place over time. And it's hard to even imagine what reality would be like without time. But despite the fact that it seems to be so deeply ingrained in everything about what we do, we have a really hard time describing it. So time is also, it's both embedded and it's also very abstract. And we've come up with all these very complicated theories describing what time is like. So the idea of time being linear and universal, continuous, observer-independent, all of these Newtonian ideas feel like common sense to us. But despite the fact that they seem so intuitive, physics itself is now telling us that maybe these are not real properties of the world. And if they're not real properties of the world, then where do they come from? And that's kind of what's driving some of the questions that I got at in my dissertation. So one thing that falls out of this is that in order to deal with the fact that our experiences of time are so subjective, and the fact that modern industrial life requires us to be in specific places at specific times, we've had to develop, and all different cultures have developed different symbolic systems for representing time in a very precise way. So this includes language, it includes clocks and calendars and timers. But given that these two things are so different, what role does our actual experience of the world play in our construction of these symbolic systems? So that's one question. And I look at this from a developmental standpoint. So the other question is just, what are the developmental origins of these very abstract adult-like concepts of time? And in my thesis, I looked at this in 3 different ways. So the first 2 chapters of the thesis are both about how children learn time-related words. So some of the first symbols that we use to represent time. The first is about duration words like minute and hour. The second is about deictic time words like yesterday and tomorrow. And the third chapter looked at something a little bit different, which is our spatial representations of time. So how do we start to think of time as being a line with a particular direction? And for this talk, I'm going to focus on these first 2 chapters. I'm going to jump back and forth a little bit because the structure is similar and the story that these 2 papers wind up telling is pretty similar. So how do we learn time words? One approach that's been used, a whole set of theories about how abstract thought might be possible, basically takes a building block approach. So this is the idea that in order to come up with very complex thought, perhaps overdevelopment, we're able to put together primitive or innate, more simple ways of representing the world in order to come up with something that's more complicated than the sum of its parts. So in the case of time, there are some ways of representing time that seem to be there from the very beginning. So even very young infants are able to discriminate durations. They can tell the difference between longer stimuli and shorter stimuli. We're also sensitive to the sequences of events that we see. Young babies can imitate things in the right order. Babies have intuitions about how temporal sequence matches up with causality. They're surprised if they're shown a video that doesn't make sense in terms of the causal and the temporal relations shown. So are these the building blocks for our more abstract ways of thinking about time? Ultimately, I'm going to argue that these things are not enough. They're not enough to get to this end system, which ultimately we all learn. By the time we're adults, we have these formal systems for representing time. So time words like minute and hour, they have these precise interrelated definitions. And of course, we're not born with these symbols. They're actually very slow to learn. So this is the proportion of kids who are able to correctly answer questions like how many seconds are in a minute. And what you see is that most 5-year-olds don't know the answers to any of these questions, and it's not really until kids are in 1st or 2nd grade that they can reliably answer questions about the exact definitions of these words. But interestingly, despite the fact that kids don't really know what these words mean in an adult-like way until they're 7 or older, much younger children are perfectly willing to talk about time. So you might ask a toddler, even a 3 or 4-year-old kid, how long did you watch TV? And get an answer like, oh, just 10 hours. And in a lot of these cases, the kids are clearly incorrect. I mean, hopefully she didn't really watch TV for 10 hours. But despite the fact that they're wrong in obvious ways, the kids are using these words in appropriate ways. So she's answering a question about duration with a duration word. So it seems like anecdotally that there might be some partial understanding early on. The same is true of deictic terms. So you might ask a child a question like, when did you get the tummy ache? And receive an answer like, it's always since after tomorrow. So this makes no sense. But despite the fact that it isn't correct, she's nevertheless using the word tomorrow in a correct context. So what these two papers are doing is they're really mining this period. This is very unusual. There's up to 5 years in between when kids first start saying these words and when they eventually comprehend them like adults. So we're going to be looking at this long period and trying to get a much more precise idea of exactly what kids know. So what do they think these words mean? How did they learn those early meanings? How did those meanings evolve over time? And from this, we're hoping to get a window into kids' first hypotheses about how time might be represented symbolically and how their early concepts of time change. So how might kids form their very first meanings for duration words? One hypothesis is that those first meanings really are perceptual. So kids are constantly experiencing events in the world, they're hearing these words used, maybe they're able to associate a word like minute with, say, the approximate length of an event like brushing your teeth, which is described using the word minute. And the same process could work with different duration words. It could also work with deictic terms like yesterday. So in this case, a parent might use the word yesterday to describe an event that the child experienced an approximate length of time ago. So you might get some sort of mapping there. Again, here's some other examples of how kids might be able to make mappings between words and events. Say you've got an event that the child is very familiar with, say a favorite TV show, and the parent is constantly saying like, no, you've been watching that for an hour, or you just watched that yesterday, or no, it won't only take a second, it takes 20 minutes. So this is giving the kid lots of different opportunities to relate these different time words to their experience of an event. So if this is how children are learning their early meanings, that makes some predictions about what they should first know about these words. So the most important thing is that they should have some sort of approximate duration associated with each word. Also, because duration perception itself follows Weber's law, they should be better able at discriminating words that differ by a larger ratio. So seconds versus years should be easier than minutes versus hours. And in the case of these deictic terms, they should have an approximate sense of what I call remoteness. So that's how long ago something was. So that's one hypothesis. Another hypothesis is that even children's very first meanings for these words are not perceptual, they're actually relational. So each word is defined by where it falls in a set of other time words that the child might be hearing. So how might a child wind up with this type of definition very early on? One way that this might happen is if you just take the event out of the picture and just focus on what the child has there in the language, there are all of these different cues that could help the child figure out, to form some hypotheses about what these words mean. So the facts that these words are appearing in similar types of sentences might make the child able to figure out that there is a whole class of duration words that all perform the same type of function. When they're being explicitly contrasted, you can get a sense of the general ordering of these things within a domain. All else being equal, we usually talk about events and the order in which they occur. So if words like yesterday and tomorrow are being used, they're often in that relative ordering. And of course, grammatical tense can give us a sense of whether deictic terms refer to the past or the future. So if yesterday is always being used in context with the past tense, then you might be able to infer that it refers to the past. So if this is how children are learning these words, this makes different predictions about what they should know early on in their acquisition. So the first thing is that they should know something about the relative ordering of the words. They should also acquire the words in relative synchrony. So in this case, because these words are interdefined, your knowledge of one word is going to be limited by your knowledge of the whole set. And importantly, you should not have understanding of the approximate duration associated with each word, because that you're actually not getting from the language input. So none of those quotations I put up there would give you a sense of approximately how long an hour is. All right, so how do we test this? The first method we used is a very simple one. We just told kids that there were characters who did events for different amounts of time. So Captain Blue slept for a minute, Farmer Brown slept for an hour, who slept more? So this just gives us an index of whether the kids know anything about the relative magnitude of these. And what we found is that even 4-year-old children, so these are children who are making lots of errors in speech, are above chance at contrasts like this. We didn't find differences across words, and we didn't find ratio effects. But what's even more interesting is over on the right, we changed the paradigm to include number words. So in the case where we have no numbers in there, you could do that based on knowledge of the ratio, you can do it based on knowledge of the order. But in these cases where you've got number words, and especially when the number words give you incongruent clues as to which one is bigger, in order to know that 2 hours is actually bigger than 3 minutes, you have to know something about that ratio and the fact that it's much larger than 3 to 2. So if kids have perceptual meaning, they should be fine with this. They should do equally well. But if they only have relational meanings, they should do worse on these incongruent trials, and they should focus on those number words that they know better. So what did we find? So the critical trials are in red. These are the incongruent ones. And what you can see is that these are indeed a lot harder for children. Up until kids are about 7, they're really getting stumped by these cases where you have incongruent numbers and time words. So just to give you a quick summary of what I've told you so far about time word learning, it seems that kids know which duration words are bigger, but they don't know how much bigger. The aspects of meaning that kids learn earliest are those that are most readily inferred from their language input alone. And this supports the hypothesis that relational meanings for these words actually precede perceptual meanings. But there are some limitations to this very simple paradigm, so I also wanted to tell you about a different method that we use to look at partial understanding of time words. and that's a spatial timeline. So timelines are really cool because you can use the exact same data to index children's knowledge of different facets of meaning for time words. And you can do this with duration words, but you can also do it with words like deictic terms like yesterday, today, and tomorrow. So I'm going to kind of switch over to that mode and tell you a little bit about that study. And interestingly, different learning strategies for these words are going to predict different developmental trajectories for children's partial knowledge. So which pieces of the meaning are they acquiring earliest? So how does the timeline method work? This is pretty simple. We just give a kid a spatial timeline. We explain it to them. We say, this is a timeline. It goes from the past to the future. So it goes from when you were a baby all the way to when you'll be a grown-up. And right now is here in the middle. So we always point out the present as well. And kids are given colored pencils, and we give them a series of time words and events to represent on the line. And the way we code this is interesting because we do it in 3 different ways. So on the top, we code the relative ordering of the terms. So just do they know that last year should be to the left of yesterday, irrespective of where they are with respect to the center of the line or how they're spaced. Secondly, we looked at their deictic status or their past-future status. Just are they putting yesterday on the left in the past or are they not? And third, we looked at remoteness. So this is an index of how well the kids are spacing these terms relative to right now. So we looked at children's acquisition of all 3 of these elements of meaning. If kids are using language, like I said earlier, you would expect them to have some knowledge of relative ordering and of deictic status early on. But if they're using events, you'd expect them to have some knowledge of approximate remoteness early on. So what did we find? I'm going to show you the median locations for where children put a series of time words on the line. So age is going up with 3-year-olds on the bottom, going all the way up to adults. And what you can see, if you focus on the youngest kids, is that they're really all over the place. They're making mistakes with the order, they're making mistakes with the past-future association, and the spacing isn't right. But by the time kids are 5, they've pretty much got the ordering set. They've got the past-future status set. And at that point, it's only the remoteness which continues to develop over time and become more adult-like. This is another way of looking at it, which just gives you the average age at which kids are making a transition from non-adult-like to adult-like performance. And on both the past-future associations and the ordering, this is happening in between their 5th and 6th birthday. So over half of kids are doing this in an adult-like way by the time they're 6. But with remoteness, it's lagging behind by almost 2 years. So it's not until after kids turn 7 that they're doing this in a more adult-like way. So what can account for this? How are they finally understanding remoteness? One clue actually goes back to our study on duration words. We found quite a similar pattern here. In this case, we gave them timelines going from a short amount of time to a long amount of time, but we found the same pattern where kids could represent the relative orderings around the age of 5 or 6, but they couldn't space these things out appropriately until they were beyond the age of 7. And in this case, we actually modeled kids' ability to do this task, taking into account their knowledge of the exact definitions of the words. So the very first data I showed you at the beginning. And it turns out that their knowledge of those definitions completely accounted for the effective age. So it seems like this piece of the puzzle, this ability to represent the proportional relationships between these words, the approximate durations, doesn't come online until after kids have been formally taught the definitions. So just to summarize, our data about children's acquisition of time words shows that they have partial but systematic meanings for these words during this long period between the time where they first start saying them and the time at which they have adult-like meanings. During that period, they first infer their relations, so the fact that all duration words are members of a common semantic class, Secondly, they build an ordinal structure. So this is when they're figuring out the relative ordering of terms. Next, they learn the formal definitions in school, and it's not until after that point that they seem to be able to map these things to perception in a reliable way. I'm going to skip this because I don't have time for it. But in conclusion, what we're finding from these studies about time concepts in conjunction with some of our studies showing that spatial representations of time are also very slow to develop is that these concepts don't seem to be constructed from perceptual primitives that are there from early infancy. Even in the beginning, they are a separate symbolic system, which is ultimately used to organize and explain perception. And this is something that's initially constructed from linguistic and cultural input in early childhood. And many people are to thank for this, but I just wanted to focus on my lab at UCSD, who are really, really wonderful. My advisor, Dave Barner, is pictured in the middle. But now that I have my own lab starting up, I really, really appreciate how fundamental all my lab mates were to making the dissertation happen. So thank you very much.